I've done some previous videos on 3D printing, but that was mainly for outreach activities. And in essence, 3D printing is creating a 3D object from a 3D model, usually using a CAD, so a computer aided design. So the question I've been getting then is, why don't we use these 3D printing for bioreactors, or how often is it actually used in the pharmaceutical industry and what are its drawbacks? And this is exactly what I'm going to discuss in this video. And key things here I will touch upon is like what we can achieve nowadays with 3D printing. So what kind of geometries can we achieve? The leakage will be a problem for certain techniques, and also touch upon the sustainability. And also touch upon the sustainability, because generally you create less waste when you use 3D printing, and you can even 3D print from renewable sources. So that's why this might be very appealing, especially when you use it single-use bioreactors, where you can look at other materials going beyond, for instance, glass or just traditional stainless steel. Now, obviously, there's many different types of 3D printing. So generally, people class it into around 7 different categories. There's some debate in how many different categories there actually are. But for the purpose of this video, I'll look at the ones that are most commonly used, and I'll look at a specific paper where they actually compare these 3 methods. So the first is stereolithography, where they use liquid materials. So there you use some UV polymerization to go from the liquid material to the solid state. And that generally leads to the production of very robust materials, and it's got a very good resolution. However, this is a little bit smelly, so we use this very routinely in the lab. It's probably not something that you would want to use at home without having like an exhaust available. The second method, so fused deposition modeling or fused filament fabrication, FFF, that's probably the most popular method if you want to be using this at home, because it's the simplest. You just work with like a layer by layer process, so you build it up one layer at a time. It's just plastic. You do need to heat up things a little bit, but it doesn't have that very typical smell that you get with the resins that you use in stereolithography. However, like it's not as accurate as stereolithography, and because you do print it layer by layer by layer, you can get some leak. And because you actually print it layer by layer, you can actually get some leakage in between the layers. So you need to very carefully consider the infill, or there are some alternative techniques to close the pores in between. In my lab, we simply use some nail varnish, which also kind of helps to close out the gaps. But you can imagine that's not large scale, where you're dealing with larger volumes or, for instance, higher pressure, which can even lead to more leakage. Now, the third technique I'll be looking at is selective laser sintering, or SLS, where you use powders, and there you can The third technique I'll be considering is selective laser sintering, where you can use powders in combination with a binder, and you remove the binder afterwards. So this has the advantage that it can be used from metals, because we do know that a lot of actually the bioreactors on a bigger scale do use metals. However, you will see this is much more time consuming, because you will need to remove the binder afterwards, and is much more expensive. So it doesn't have some of the inherent advantages that you get with method 1 and 2. Now, before going on to comparing this for a specific bioreactor, I'll have a little look at the history of 3D printing, so you can get an idea of what's been achieved in a very short span of time. So 3D printing was more or less pioneered in the 80s, and the first business was started around 1988. The 3D printing was more or less established in the 1980s, with the first going into business in 1988. And then you will see the rise of some of these other methods, such as SLS, which really expanded the scope of the materials that we could be using. Initially, 3D printing was mainly used for prototyping because it's very rapid, but it didn't have the same material properties as using other techniques to build things. However, this started to dramatically change when we started to look at, for instance, bioprinting. So you can see here that the first artificial bladder was printed in 2011. So we were able to embed a lot more functionality into these materials, the use of metals. And then already 2016, so 8 years ago, we were able to build the first habitable 3D printed structure. So what's really changed 3D printing is obviously when the pandemic response came into play. It was very vital to produce a lot of personal protective equipment. So then people started to really see the benefits of these techniques because of its rapid and low cost nature. Because it's very simple, there's a lot of designs available, you just can go to certain websites to download them, and then you would be able to print everything yourself at home. So let's go back to how we can use that then in bioreactors. Now, I looked at this particular paper, and what they did there, they chose a specific design for a bioreactor, and they compared it with the three different techniques, so SLA, FFF, and SLS. And what they also did is they looked at different printers, and generally they could see that for every specific printing device, you have to optimize your parameters. So it's not just about the different technique that you're using. The individual printer has a big influence. And you can also see there's a wide variety in the prices of 3D printers. You can buy really, really cheap ones online. The FFS ones are typically by far the cheapest, to more sophisticated models. Now, on the top, unlike A, you can see they looked at the accuracy and they were comparing the three different ones. So both the X, the Y, and the Z axis. So generally, and we already know this, is that SLA tends to have the highest accuracy, particularly if we look at more sophisticated geometries. So if we look at more difficult shapes. So you can print up to like micron resolution with that. Then the other thing that people started to have a look at, which is very important, is this leakage that I touched upon first. So I mentioned there are like techniques to reduce leakage when you use FFF, but you might have to use some evaporation techniques, so they add to additional costs. You might have to really increase the infill. So it doesn't really benefit because FFF is supposed to be like a really cheap printing technique. And then if you need to add something else to it to optimize this, that doesn't help for the purpose. And particularly in bioreactors where you might be using higher pressures, this can be a real problem. Another thing to consider is, because these materials are porous, that you might get some absorption of specific things into your resin, which you then can't wash out. Another thing that they concluded, that FFF and SLA are by far the faster printing techniques. They're also the cheaper ones compared to SLS, where you have to remove the binder afterwards. So you can see However, the unique opportunity with SLS is that you can consider metals, which you can't necessarily do with the other techniques. So there's a lot of things to kind of consider here, but the accuracy and the ability to actually print the geometry that you need, that's not something that's holding it back from necessarily using it in 3D printing. There's a lot of things to consider here, but actually the geometry and the resolution and also the cost, these are not really specific drawbacks when you want to consider it for using it for a reactor. However, if you are considering it for healthcare applications, sterilization and being able to clean your material, that is a big problem. So what they considered in this paper as well is they looked at these 3 different techniques and they autoclaved the material. So in essence, you need to heat it up to over like 100 degrees and they checked what happened with the tensile strength and the flexible strength. So what they did see is that FFF, the flexible strength, is definitely impacted by autoclaving. So here they looked at 3 different times, so you can see that it generally kind of goes down after that. So here they only considered 3 different rounds of autoclaving, and that's why they concluded that until now these 3D printing constructs are probably best for single use. However, they found with the other 2 techniques of SLS, the other techniques at SLA and SLS, this wasn't much of a problem. But please do consider that when you're using these materials, that all of this is very highly material dependent. So it won't just depend on the technique, but it will also definitely depend on the material that you're working with. So kind of issues that you might consider here, because even if you have it for single use, you probably want to like sterilize your material before you actually start the reaction. So what you would be concerned about that there might be some leaching of the material going into the bioreactor itself. So the fact that you're maybe not able to clean it as well as you can with, for instance, which is a big advantage of stainless steel, this might actually hamper this particular application. But what they did find in this particular case, they looked at a small scale application, particularly for tissue engineering, where you are mostly working with disposable systems. This is where 3D printing might find its niche application. However, until now, this is far more common in a lab environment, where we, for instance, also employed this, compared to, for instance, use in industry. So what could be an advantage of this is that you could use this as prototyping again, where you would consider printing different types of models and you would see what the impact of the different geometries or the different shapes is on the performance of the reactor. So the general summary that they drew into this paper, so SLS, we know it's the most expensive. It also happens to be the least reliable when it comes to having a very specific geometry. And another big disadvantage is that it requires extensive post-processing. However, it does enable you to use specific materials that you can't use for the other methods. So it seems that SLA is the best method for printing of complex geometries, which you might certainly need in reactors. But FFS has by far the lowest production cost. So here, like what you have to consider, we mentioned the issues around leakage, especially if you might consider high temperatures and, for instance, high pressure. So it is best to consider this system for single use and to check whether you're not introducing impurities in your system. So besides looking at the different 3D printing techniques, you will need to optimize your system per printer that you're using. So it really depends on what you're using in the lab. And you will need to consider things like sterilization and autoclaving and how that impacts on the properties in case you want to use it for this application. However, like here I've mentioned lots of perhaps downsides. If we think of the sustainability impact, this will definitely bring benefits. So you can use things like such as, for instance, recycled materials. You can use things like, as for instance, recycled materials. And generally, we know with 3D printing, there's less waste produced than with lots of other production methods. Another thing to consider is particularly the lowering of the costs, because you can use very low cost materials. And it gives you a lot of flexibility. So particularly in certain areas in the pharmaceutical industry where you're not producing something like bioethanol or things which are produced on really large scale, that might give you that versatility and flexibility. But until now, you will see that most of the time this 3D printing is used to consider different prototypes. And even then, it's not really used in industry that much. It's mainly limited to use in the lab. Thanks for watching, and do have a look at our playlist where we consider different types of bioreactors that are used. Thanks very much for watching, and we do have a full playlist where we look at different types of bioreactors that can be produced, for instance, using these 3D printing techniques.